Now I'm talking about branched projective structures. So the definition is as follows. So I write BPS for branched projective structures. A branch projective structure on S is like, for a projective structure, it is an open covering of S and maps phi i's that are not local diffeomorphisms, but they are locally ramified, not far from being diffeomorphisms. There are locally ramified coverings, phi I from UI to CP1. So locally ramified coverings mean that they look like the map Z goes to the Z n+1 from C to C. Away from 0, it's a local diffeomorphism, but at 0, all the leaves collapse. Such that, so it's still the same condition, phi I, it is Gij composed by J on UI intersected Uj. So, example, take S prime, another surface, and UI phi I, an unbranched projective structure, so a regular projective structure on S prime. And let F from S to S prime be a ramified covering. Then if you take the inverse image of the UIs by F, it is an open covering of S. Hence, if you take the phi i's composed with F, these are locally ramified coverings. So this atlas is a branched projective structure on S. So this shows that the notion of branch projective structure is much more flexible than the notion of projective structure. If you want to pull back a projective structure, you need a covering. If you want to pull back a branch projective structure, a ramified covering is enough. And of course, ramified coverings are much more, there are much more ramified coverings than only just coverings. Okay, so now a branch projective structure on S, it still defines a complex structure. On S, but it also defines a branching divisor D, which is the divisor of ramification of the charts of the branch projective structure. Namely, the divisor is the points of, so a divisor on a surface is a collection of points along with multiplicities, and here the divisor D is the points where the charts of the branch projective structure ramify, and the multiplicity is the multiplicity of the ramification. So the multiplicity of Zn+1 is n. and a branching degree. So a branch projective structure has a branching degree, which is the degree of the branching divisor, degree of D. So let me introduce the space Tn of S. It is the space of couples XD, where X is in the Teichmüller space and D is a divisor of degree n on X. And Pn of S is the space of marked branched projective structures on S of branching degree n, quotiented by isomorphisms. And so like in the unbranched case, there is a forgetful map. That I write Teich n from Pn of S to Tn of S. And now, so as I said at the end of the first part, let me now introduce the holonomy map. So as I said, the proposition of Riemann adapts in the branched case. So a branch projective structure on S is the same as a couple PS. I will take a branch projective structure on X. I take X in the Teichmüller space. This is a couple PS where P flat CP1 bundle on X and S is just a non-flat section of P. So as a consequence, there is still a forgetful map. From Pn of S to the character variety, seen as the right moduli space for flat CP1 bundles. Okay, so now what's the question is, does this nice feature of projective structure, namely that their moduli space has a nice complex structure, a nice structure of a complex manifold, is it still true for this generic case of branched projective structure? First, we can look at the two ways that we got a complex structure on P of S, namely copying the complex structure of the Teichmüller space and copying the complex structure of the character variety. So for the Teichmüller space, Tn of S, it is still a complex manifold of dimension so 3G minus 3 dimension for the X and n dimensions for D. So 3G minus 3 plus n. But now
so Gustave, your divisor is reduced?
No.
Definition of Teichmüller, no?
No. I don't take a reduced divisor. It can be any divisor.
Anything. Okay, of degree D.
Of degree n, yes.
N, oh, sorry. Thank you.
So the problem is that the Schwarzian parametrization doesn't work that well. The Schwarzian parametrization was the fact that we could take the difference of two projective structure and it was a nice global quadratic differential. But here, so I write, so I take x in x, say xd in Tn of s, and I write pxd is the holomorphic branched projective structure on X of branching divisor D. So it's the inverse image of XD by Taish N. And the point is that if I look at all the differences P1 minus P0 with P1 and P0, P0 in PXD. So it is still possible to compute this difference, and it will give, in fact, a meromorphic quadratic differential. But this space is not. There will be conditions on the meromorphic quadratic differential so that it is a difference like that, and so this space is not a vector space. It has not a natural structure of vector space. So it's not as nice as for projective structure. There is still a theorem that by Mandelbaum. He's the guy who introduced branch projective structures. And he says that PXD is an analytic space. So there is condition, sorry. If n is smaller than 2g minus 2, or the divisor D is supported on one point. So D writes nx for some x in the Riemann surface x. Then PXD is an analytic space of dimension 3g minus 3. But we don't know if it is smooth, and we don't know how it deforms. We don't know how to glue the difference, the different space PXD when X and D vary. So it doesn't allow us, especially there is especially a difficulty when D is not reduced. So this doesn't allow us to put a complex structure on Pn of S. And now let us look at what happens on the side of holonomy. So here there is a theorem by Calzamiglia, much more recent theorem by Calzamiglia, De Rouen, and Francaviglia. It states that if you fix a flat bundle rho in the character variety, such that rho is in the smooth locus. So it is in the smooth locus. It's not. It is not singular. Is not singular. Then the inverse image of the holonomy map inside a Pn of S is a complex manifold of dimension n. So the fact that these fibers, so we have here Pn of S and X of S, the fact that this fiber of this map over the regular points of the character variety are smooth, are nice complex manifolds of dimension n, it is a clue that Hol might be a nice submersion from between complex manifolds, because the fibers of a submersion are all the same dimension and they are complex manifolds. But the problem is that for n high enough, there are branch projective structures whose holonomy is a singular point of the character variety. And Calzamiglia, de Roy, and Francaviglia don't know what the inverse image of a singular point looks like. So the theorem I want to present, let me write it again. It is saying that Pn of S is a complex manifold of dimension 6g minus 6 plus n, and the maps Taish n, so the maps to the Teichmann space and to the character variety are analytic. And moreover, so there is an intermediate variety. There is complex manifolds An of S, that is a manifold of what I call branching classes. So An of S is so it's of dimension. The dimension of An of S is 3g minus 3 plus n. It is an affine bundle over Tn of S, the Teichmann space with the divisors, and there is a map from Pn of S to An of S alpha. And the last point is, and so so in fact, the complex structure of Pn of S comes from the complex structure of An of S, and there are two extreme cases. If n is smaller than 2g minus 2, alpha is an affine bundle. So Pn of S is bigger than An of S, and alpha is a bundle. if n is greater than 4g minus 4, alpha is an embedding. Sorry, I made a mistake. The dimension of an of s is 3g minus 3 plus 2n. So when n is small, clearly 6g minus 6 plus n, the dimension of Pn of s, will be bigger than 3g minus 3 plus 2n. And so it makes sense that Pn of s is an affine bundle over An of s. But when n grows, the 2n will be very high. And so 3g minus 3 plus 2n is bigger than 6g minus 6 plus n. And so it makes sense that Pn of s is an embedding and a submanifold of An of s. Okay, so let me give a clue on the proof now. So first I will explain what this manifold is. So branching classes. So a branching class can be seen as the infinitesimal description of a branch projective structure at the branching points. So the remark, so yes, the space I'm interested in, I write it Rx n tilde. It is the space of, so I take X, a Riemann surface on S, and little x, a point of X. And Rx n tilde, it is the germs of ramified coverings from the germ of big X at little x to the germ of C at 0. So phi is an n plus 1 sheeted ramified covering. And so I take, of course, the germs here. And there is an action of the automorphisms of the germs of biholomorphisms of C at 0. This acts on Rx n tilde by post-composition. And now the facts that is at the base of the notion of branching class is that the action, so if n is greater than 1, the action of the group of germs of automorphisms of C at 0 on Rx n tilde is not transitive. So there is a space of orbits. So this is quite easy to see. Take phi1 and phi2 in Rx and tilde. So for instance, phi1 of z is z n plus 1. Phi2 of z, it is z n plus 1 plus z n plus 2. These are two n plus 1 sheeted ramified coverings. And take any gamma in the group out of C0. So gamma you can write gamma of W, it has to be 0 at 0. So it is A1W plus A2W square plus etc. And if you make gamma act on phi1, this will be gamma of phi1 of z, and it is A1 zn plus 1 plus A2 z 2n plus 2 plus etc. And it cannot be phi2 because whatever you choose for gamma, there will not be terms of order zn plus 2. So this is not phi2 of z, and thus you see that phi1 and phi2 are not in the same orbits under the action of OT C0. So the action is not transitive. So in the framework of branched projective structures, the phi's here, the phi's from X to C0 that are going to represent the germs of charts of a branch projective structure at a branch point. But of course, the group that acts by postcomposition on charts of branch projective structure, it is not the whole group of automorphisms of C at 0. It is only PSL2C. So it is PSL2C that acts by postcomposition on the charts of a branched projective structure. And an element G in PSL2C is determined by its two jets at 0. It's two jets at 0 that we write J square 0 of G. So this means that G is determined only by G of 0, G prime of 0, and G seconds of 0. Thus, the group that we look like is not the whole group of automorphisms at 0, but a quotient of this group. We only look at OT2 of C0. It is the two jets at 0 of elements of OT0. And this, why? Because this group is actually the same as the subgroup of PSL2C of elements that fix 0. And of course, this group doesn't act on the whole Rxn tilde. We have, in order to have an action of OT2 of C0, we have to take jets of ramified coverings. And in fact, we put Rxn, it is the two n+1 jets. This is the right order to take in order to have a free action of OT2 of C0. So the two n+1 jets of phi, where phi is a n+1 ramified covering from XX to C0. And then we write the space of branching classes of X at zero at X of order n. It is the space of orbits of this action. So it's Rxn quotiented by OT2 of C at 0. Okay, and so this is the space of what they called branching classes of order n at X. And now take D, a divisor, say of degree n on the Riemann surface X. So D writes sum of I1 to R of Ni Xi. It is a collection of points of X with multiplicities. And put AXD, it will be the product for I going to from 1 to R of the A Xi and I. So you take the branching classes at the points of D with order the multiplicity of X I as a point of D. Now, if you take P, a branch projective structure on X of degree D, so little p, then P determines a branching class alpha of P in AXD, because you just take the class of the charts of P at the points Xi, at the points of D. And now the proposition that makes branching class relevant for studying the moduli space of branch projective structure is the following. So first, AXD is an affine space directed by H0 of X Kx restricted to D. So this is the an element. So this is the jets of differential holomorphic differentials on X at the points of D, and it is of dimension n. Okay, points of D. And second, if you take P1 and P0 in PXD, so branch projective structure on X with divisor D, that have the same branching class. So alpha of P1 is alpha of P0. Then you can compute the Schwarzian difference, and it is a quadratic differential vanishing on D. So you find again a nice, a fine structure on the space of projective structures, branch projective structures. But what you have to fix is not just the Riemann surface, not just the Riemann surface plus the divisor. You need to fix also a branching class in order so that the Schwarzian parametrization is nice. Okay, and now the space A n of S that I mentioned in the theorem. It is you just take the disjoint union for xd in Tn of S of AXD. So of course the dimension of AXD, it's the same as the dimension of H0 of x kx restricted to D, and it is n. This is n whatever the divisor D is and whatever x is. And so we have the following proposition. The spaces AXD glue together so that AN of S over Tn of S is an affine bundle. And thus AN of S is a complex manifold of dimension. So the dimension is the dimension of the base. So the dimension of Tn of S is 3g minus 3 plus n, plus the dimension of the fiber, and the dimension of the fiber is n, so it's 3g minus 3 plus 2n. Okay, and so we have a map alpha that's to a branched projective structure associates a branching class. So now we have this complex structure on AN of S, which can be seen as the space of infinitesimal branch projective structures at branch points. And the question is, how do we get a complex structure on the space of global branch projective structures? How much time do I have?
You still have 8 minutes.
8 minutes, okay. So I will give a clue on how to go from infinitesimal branch projective structure to global branch projective structure. So take A in AXD. The difference between the complex structure between the infinitesimal the infinitesimal branched projective structure A and a global branched projective structure on XD is described by two phenomena. By first an ambiguity. So knowing an infinitesimal branch projective structure, maybe it's not enough to know with certainty the global structure. So there may be A may extend to several global branch projective structure, and this is governed by the H0 of by this space, because if alpha of P1 is alpha of P2, P0 is A, P0 minus P1, we know where their difference lives. And there is a second phenomenon, which is an obstruction. Maybe A does not extend at all, might not extend to a global branch projective structure. And in fact, this is so there is an obstruction. C of A, and it is classical, at least in algebraic geometry, when we look at structures whose difference should live in the global sections of a sheaf. So in the H0 of a sheaf, then the obstruction to the existence of such structure, it belongs to the H1, to the first cohomology group, and it is the case here. The obstruction to the existence of a branched projective structure whose branching class is A, it is in the H1 of the global quadratic differentials that vanish on D. So of course, this means that C of A is 0 if and only if alpha minus 1 of A is non-empty. Okay, so now recall the Riemann-Roch formula. It says that the dimension of the fiber, so H0 of kx square minus D, minus the dimension of the space of obstruction, it is the degree of the bundle. So the degree of kx square is, no, it's not the degree of the bundle, it's 3g minus 3 minus n. Okay. And so there are two interesting cases. Case A is when n is strictly smaller than 2g minus 2. Then the H1 of kx square of minus D, it is the same by Serre duality as the H0 of x tx. And this, we saw that it is, tx of D. But the degree of tx of D, it is n minus 2g minus 2, which is strictly negative in this case. So So the H0, a bundle with a line bundle with strictly negative degree has no section, so the H0 is 0. And so the H1 of x kx square of minus d is dimension 0 for any a, and this implies that C of A is 0 for any a in an of S. And moreover, the dimension of the fiber alpha minus 1 of A is the dimension of the H0, and it is exactly 3g minus 3 minus n, which is independent on independent of little a. So we have this map alpha from Pn of S to An of S. We know that it is surjective because there is no obstruction to lifting a branching class to a global branch projective structure, and the fibers are all affine spaces of the same dimension. And in fact, in this case, we can show that Pn of S is an affine bundle. And the other easy case, it is when n is bigger than 4g minus 4, then it is reversed. The degree of kx square of minus d, this is 4g minus 4 minus n, strictly negative. Thus, the dimension of the H0 is 0. So the fiber, so alpha minus 1 of A is either the empty set or a point. And this says exactly that Pn of S is a subset. Alpha is an injection. So Pn of S is a subset of An of S. And moreover, the dimension of H0 of the obstruction space is n minus 3g minus 3, and it is independent on A. And this means that there is a vector space, a vector bundle V ops over An of S, whose fiber over a class over A in AXD is this space. So in order for such vector bundle to exist, a necessary condition is that the dimension of the H1 of all the fibers of the vector bundle has to be the same, of course, and in fact it is sufficient. And in C, you can see C the obstruction as a section of the ops, and it is an analytic section. And in fact, Pn of S is the vanishing locus of C, and thus it is an analytic space. Okay. And so in the other cases, so n is between 2g minus 2 and 4g minus 4. It's a trick. You have to inflate artificially An of S, and you go back to case B. But these are the two.
So the structure of Pn of S in the second case can be non-reduced.
No. It's so this is not the end of the proof. Actually, it is. Then you need to show that it is smooth.
Ah, okay. Okay.
Smoothness of P of S. It uses small deformations.
Okay, so you calculate the dimension of the tangent space and you prove
Yes,
that.
you show that the tangent space is the H1 of the infinitesimal automorphisms, and
Okay.
it is always the same dimension. So this
Thank
is
you.
the theory of Kodaira, Spencer, and
Yes, thank you.
Kuranishi. Okay, so I'm done.
Okay, thank you very much, Gustave, for this nice talk. So, are there any